My name is Güneş. I'm a postdoc currently at the University of Oxford. I work in the area of probabilistic programming. So I'm going to talk to you about probabilistic programming in stochastic simulators. So I would like to start with a little bit of introduction about what is probabilistic programming. So I want to make this comparison between deep learning and probabilistic programming to make a few points. So in deep learning, basically you have this like neural network black boxes that you fit to data. These are function approximators or differentiable transformations mapping inputs to outputs. And people say these are black boxes, but in fact they are not really black boxes. They are like they are differentiable programs with known stuff, like known structure. We know what they are. We know how they work. We know what is inside the neural net. But the thing is, they are not really interpretable. When you train like a very deep, high-dimensional transformation between two things, it's very difficult to interpret what's going on, even if they are doing a task very well. To contrast with this, so in probabilistic programming, instead of doing model learning between given, like model learning from data, you work with a given model. So you have to have a model, like somebody has to define a model in order to do probabilistic programming. So you basically define a probability model, and you do inference in this model to explain data observations. So this is like the most basic thing I have to start with. And this type of thing is inherently interpretable because by design you know what's going on. So you know how to define. You have an idea of like what's going on in the phenomenon that you are studying, and you are able to write a model for it. This implies that you know like the latent structure, and you can encode these things as a model. These models, the probability models, they define a joint distribution between latent and observed random variables. So in the prop community, people have this convention of having x as the latent variables and y as the observed. Just like in other places, people use z and x, I guess. So just one thing to mention. So some of you are probably familiar with graphical models, where you define a probability model by using graph structures. These graph structures represent the conditional dependencies between random variables. So by looking at the graph, you can see the factorization of this joint probability distribution. Bayesian networks and Markov random fields are examples of this. So the idea in probabilistic programming is to generalize that into general purpose programming languages, so that you can use a regular programming language to express probability models. And these models basically define a generative process, which when you run, it gives you one instance of the phenomenon that you are modeling. And this works by like it's usually introduced with this type of sentence where you say it's ordinary programming with two added constructs. These constructs are sampling and conditioning. Usually they are called the sample and observe statement. So the first one is the easy one, like it's very obvious. If you have any type of stochastic code, you basically draw random numbers from a distribution. So you do that. In probabilistic programming, what you do in addition to that is you do some bookkeeping. Every time you draw a random number, you do some bookkeeping to remember what was sampled, from what type of distribution, at which location in your execution of the code, in order to be able to do inference later on. So that's what's happening as a side effect. In the conditioning part, basically you are saying conditioning is another version of sampling where you know what is the sampled value. It's a bit indirect and difficult to explain, but basically you define a distribution and you are saying I have this observation from this distribution, and you are accounting for the log probability associated with drawing that value from that distribution. So I will try to make this clearer in the coming slides. I have this little example here where you like the one on the top is where you have two sample statements. I mean, they are not. I mean, I don't have the word sample here, but this is like a sampling from Bernoulli. So you sample the C1 and C2 from Bernoulli coin flips, and you return this tuple of the sampled values. So this thing, when you run, basically is a generative model where you get these tuples of booleans. So if you think about the whole thing, this is like 4 different values that you can get. So you have a distribution over these 4 values. The one on in the bottom is a version of the same with the conditioning added here. So the effect of this conditioning is you observe that either of these values are true, either C1 or C2. This implies that this basically conditions or restricts the execution to exclude the case where both of these are false. So the distribution of the C1, C2 tuples from this one is different from this one. So this thing is called the prior of this generative model. And when you run this with this extra observed statements, you get the posterior distribution. So this is the little introduction of what these things can look like in practice. So basically, when you have such a model available, the thing you do with this is you have observations y, and you basically explain some given data instances y in terms of posterior distributions over your latent values x's, and basically you do posterior inference to get a posterior over x given y, and you may be familiar with this, but like the actual thing that is happening in probabilistic programming is I mean, it deserves some little bit extra explanation. So the thing I'm trying to show here is so basically you run your probability model many times. So this is an instance of inference where like you execute all these sample statements in your model, like all these p(x)s are priors over your latents, and you also execute your observed statements, as many as you have in the model. And what this means in practice is at some points in your program you define distributions over data conditioned on some subset of your latents, and you get your real data that you condition on, and you make this conditioning that I was trying to explain before. You say that you compute the likelihood of the real data under the distribution of simulated data. That's basically the conditioning that you are doing. And one of the things you can do for inference is you can record these execution traces. So you run this many times. Each time you get different values for your latents, and you keep track of these, and you assign a weight to each trace. Each single trace gets a weight, and the simplest thing you can do is to assign this weight to be the likelihood of your data under the executed trace. And if you do this, this is an important sampling inference engine specific for probabilistic programs. And with this, basically, you get an approximate posterior where I mean, you have these sampled x's. You have a mixture of Dirac delta distributions over these, and you can, in practice, approximate integrals or like evaluate expectations of functions under your posterior by using these weights of execution. This is just one of the things you can do. This is importance sampling. There are different inference engines that work in different ways. So not all of the inference engines have this weighted sampling thing in it. So an interesting thing is, so this inference procedure can be seen as a reversal of the generative model. Here I'm trying to show an example from particle physics, which has been the main thing we've been working on. So the thing on the top is a simulator or a series of simulators that generate a particle physics event. So you have some simulator piece which implements some part of the standard model of particle physics. You have a particle detector piece, and basically this thing is a chain of simulators. When you run once, like one execution produces a particle interaction and simulated data coming out of it. So this is your simulator, like the joint distribution of latents and the observables. Latents being so the observed being the simulator particle detector data, and the latents everything else with any prior over them. So when you do inference in this, it means ultimately what you want to do is to have the real system. This dashed line is supposed to divide the reality from the simulation or modeling world. So you would get the real data from a real simulator, and you will put that in as the observation, and you evaluate the likelihood of that under the simulated data distribution. So by doing this, you get you basically reverse this generative process that is going in this direction, like your forward model. You reverse it, and you get distributions over all the inputs and the Laytons given some conditioning on the output of the simulator. So this is also the reason we call this whole project Atılım. It's simulate spelled backwards. It's like you have a forward simulator, you can invert it through probabilistic inference. So here, this is the point where I'm supposed to give you a little demo of how these things look like in practice. So it's here actually. I think. Oh, sorry, it's already. Yeah, it's here. So this is a little Newtonian physics simulation where you have some balls bouncing. It's basically using a Python game engine for simulating physics. And this is like the whole code. So this is the part where you define your probability model. I don't want to go into much detail, but like so you can see that I'm defining priors over things like ball radius and the elasticity, and like so there are a series of bumpers which you should. Oh, this is dead. So let's revive it. Yeah, so this is how the thing looks like. Yeah, so there are these bumpers, and I have a distribution over the number of bumpers, like anywhere between these two arbitrary numbers, 2 and 35, and the bumpers location. So I define priors over these things. So every time I run this model, I get a different. Oh, sorry. I get some different thing. This wasn't so interesting, but. Yeah, this is a more complicated case. So the output, like the observable in the simulation, is like, so this thing is supposed to represent the bucket, this U shape here. So I'm counting the number of balls at the end of the simulator that ended up in the bucket. So and I condition on that number being some given number. So because the previous results died with my Python kernel, I have to run this again. So this is going to take 30 seconds to finish. So I'm sampling 1,000 traces from the prior currently. And like, this is the prior, prior probability histograms for these things. So this is like the joint probability of bumpers, X and Y locations. Number of bumpers and like stuff like that. And you see, yeah, let's rerun this. Yeah, so that's the plot. And this is like the number of balls in the bucket at the end. You see that like most of them are like with 0, but there is some behavior in the prior behavior space that gives you like different numbers of things in the bucket. So it shows you like your model covers these cases. So you can use posterior inference to like condition on this tail here, and you can get like the distributions over like these model parameters. Oh my God, what's the no? Any suggestions about what to do? No reload. Cancel. Okay. I don't know what I canceled, but I hope it's still working. So yeah, probably. Okay, yeah. What is this doing? Yeah, you're right. Okay. Yeah, so I'm running the posterior here, and I'm conditioning on the variable named balls in box being 10. So this is like, again, going to finish in 30 seconds. So when we do this, I mean, you already see the plot here. So like, if you condition on the balls being like 10 balls in the box, in the bucket, this is like the posterior distribution over these things that used to look like that in the prior. So this is like was like a broad distribution. So you see this sort of stuff because you know, like this is the source of the balls and the bucket is here. It kind of makes sense. They are kind of here. Yeah, there are different ways of doing, like, apparently there are two main ways of doing this, like with this many bumpers and that many bumpers. Maybe I shouldn't interpret so much, but
So the question, you're just relying on the random samples you generated. Some of them happen to have
exactly
10 bump, or to have 10 balls. But if it was like amazingly unlikely to get 10 balls,
yes,
you're not showing some smart way to find this.
I mean, actually, like the thing you are asking is the like the fundamental question in probabilistic programming. If your prior covers like this thing, like if it's extremely unlikely, you should have a very good inference engine to like really figure it out. But like if it's a part of your prior, theoretically you are supposed to find it. This like the whole field of probabilistic programming is giving you the tools to like sample in these tails of distributions and things like that. But it's difficult in some cases. Yes. Yeah.
Later on, there's fancy
Yeah. So.
for filling out those tables efficiently.
Yeah. Okay. Yeah. Let's move on. Yeah. So this one looked a bit different, for example. Yeah. All right. Okay. This tells me, like, because I wanted this demo to not take so long, I'm still talking about it, but like there are only 1,000 traces here. It's not a very good number. So yeah, to remind you, so this is some like samples from the prior. So this is a prior case. So I'm going to sample from this posterior. This is a case where you succeed. Another case where you succeed. And this type of things. So I would like to finish this demo by conditioning on the observation that we have 5 balls in the bucket, not 10. So the system like tries to find some things, like interesting things just before the bucket to like filter some, like have a stream like diverting into 2 pieces, and you end up having 5 things in the box. I mean, you could do this type of things with any optimization scheme, but like the purpose of the demo is to show you how you like the workflow of defining these priors and like sampling some part of the prior as your posterior by conditioning.
And the inference engine there is.
Yeah. Yeah. Sorry.
What is the inference engine there?
The inference engine is a MCMC random walk Metropolis Hastings. Yeah, it's one of the good ones. All right, so this is done. So this is how the posterior looks like for the conditioning of like having 5 balls in the bucket. If people are up for interpreting, so for the 5-1 case, we have the sort of stuff here, and for the 10, like all of them, yeah, we can try another time. So I'm just going to show you some samples from this posterior. Okay, just one. Interesting. All right, yeah, this sort of stuff. Yeah, before this dies again, let's go back to the presentation. Yeah, so this is basically the idea, and we do this like in very large-scale simulators with basically with actual particle physics simulators. We've been doing this type of things. So yeah, here I'm explaining inference engines. So in probabilistic programming, the idea is like the user of the probabilistic programming system doesn't really care about inference, ideally. You specify your model, and you can choose one of the inference engines available in the probabilistic programming system, whatever this may be. And the system is supposed to do the inference for you. You just specify your model, and you get your posterior based on some conditioning in the ideal world. So that's the aim of this whole community. So I'm like here going to basically talk about the few like common inference engines. So you can have an MCMC inference engine where you have the like probabilistic programming specific versions of this. Random walk and lightweight Metropolis Hastings engines. These are like guaranteed to get samples from the true posterior, but they have like problems like being sequential and even giving you autocorrelated samples and requiring some burn-in. Like if you have a very large costly simulator, you have a period where you have to discard initially until you converge on the posterior. So I mean, probably you are all familiar with these things. So this blue distribution here is supposed to represent the prior, and if the posterior is the green thing, basically MCMC runs this sequence of jumps. You start from a random location in the prior, and you go towards your posterior, you converge on it, and you keep exploring the space in a way that is consistent with the posterior density. So that's what's going on. You can have importance sampling-based inference engines, and you can have you can propose from the prior, meaning that you sample points in your prior distribution, and you use the weighting scheme I introduced in another slide to basically turn these samples from prior into samples from posterior by weighting them by the likelihood. So one problem with this is like low sample efficiency. If your prior and the posterior are far from each other, and like you will have low sample efficiency, meaning like in this example, for example, this thing is the closest one in the posterior space. So I mean, it's not the best thing to do. So to improve this, people, including me, we invented different techniques where you use a learned proposal distribution. Basically, you train a proposal distribution as a neural network, for example, this Q. Basically, given the instance of observation, you can have a distribution that gives you x's, distribution over x, conditioned on y, this red thing here. Which is still not the true posterior, but it's doing a better job than like in being close to the posterior than the prior. So basically, you do importance sampling again, but you sample from the proposal, and you have some terms that you account for. Basically, you have the likelihood term, and you have terms like P over Q ratios, and you get improved sample efficiency. So these are some ways of doing things. One of the reasons I have this slide here is to make the point that, like, I mean, this is a 2D example, but in probabilistic programming execution, these points, these samples, each sample represents a full run of the simulator or the model. Like, so if you have a very costly simulator where every time you run it, you have tens of thousands of things sampled from priors, each one of these points represents one such a whole execution. So this is like an interesting thing. So you don't do the samples in a parameter space, you do the sampling in the trace or the execution space. Yeah, so there are different probabilistic programming systems, like Edward and Pyra. These are kind of famous by incorporating deep learning elements into probabilistic programming systems. Yeah, the point here is that unless you have a interesting simulator that you care about and implement it in Python using PyTorch tensors or things like that, you are basically, to benefit from this probabilistic programming techniques, you are basically supposed to re-implement things from scratch in one of the probabilistic programming systems. The thing we've been working on is to define some system and infrastructure that allows you to use any existing stochastic simulator as a probabilistic program. So I'm going to explain how that works. So the idea is, if you have an existing simulator in your domain, or like physics domain or otherwise, if it's stochastic, it means it's already doing the sampling that I described. It's the first part of probabilistic programming that is already happening. So if you have a way of reaching into the simulator and like recording what type of random sampling is happening, and like recording as the probabilistic programming trace, you already like to have like most of the requirements of having a probabilistic programming system. And the second part is the conditioning. So if you introduce this like capability of defining a likelihood and conditioning on some real data observation, these two things are enough to treat any existing stochastic simulator as a probabilistic program. So you just need a bit of infrastructure to accomplish these things, and in my work we provided this infrastructure. So basically the advantage is if you are in a domain where you have a simulator that people know and trust, it's basically incorporating all the domain knowledge of like all the experts in the field in terms of the simulator, like people have in particle physics and in other scientific fields or engineering fields. So you can, even if the intention wasn't to have a probability model, you can still take in a stochastic simulator and treat it as a probability model. So that's what's happening, and this is another point to make is like this is very. I mean, the relevant part for this workshop is that this technique is interpretable. So this is very different from taking a simulator, sampling a lot of data from it, and training some deep neural network with it, and just discarding the simulator, which gives you some neural network that kind of works, but you don't really know what it's doing, or you don't know how much you can trust it, or you don't know what it's internally doing. In this technique, you don't discard the simulator, you have the simulator, and you can basically every time you get the posterior, you get the posterior by executing the simulator, and the simulator is still there. And you can see what part of the model is doing, like what part of the model is responsible for the results you are getting. I will have some graphs to show these things in experiments. Yeah, so the results are from the simulator and they are interpretable results. Yeah, so this part is about the software engineering aspects of this. I described this already. So you need a probabilistic programming system that has this thing supported. Like the system should be able to get the random number throws from other programming languages or other executed systems. So basically, I implemented 3 pieces. So there's a probabilistic programming library called PyProb, and this protocol thing in the middle is that we call PPX is a lightweight protocol defining probability distributions and sampling operations. So that if you can connect your simulator to this PPX execution protocol, basically by taking the random number generator in your system and connecting this to the protocol, you are able to execute your simulator as a probabilistic program. And yeah, the last bit is like the part you have to implement for the simulator to connect to this. Yeah. Yeah, so PyProb is a PyTorch-based probabilistic programming system, and it has these inference engines implemented currently. So yeah, these 2 are the families I described before. And so there is this technique called inference computation that we've been working on. It's a way of using deep learning to make importance sampling more sample efficient. So I'm going to briefly describe how it works. So basically, so the thing on the top here, this box, is representing your simulator. These are your latent samples, like, and the number of samples in each execution can be different. So like this is completely open-ended. This is why it's called universal probabilistic programming. Every time you run your simulator, you have a series of latent sampled, and you have a designated observable y. So you sample many such traces, like millions of these traces, and you train a neural network to basically invert this thing. You take, like, from each x-y pair of simulator executions, you take the y, you make it an input to a neural network, recurrent neural network. So in the work I'm going to describe later, we have like a 3-dimensional observable. So we pass that through some embedding, like a 3-dimensional convolutional neural network. And basically you have an LSTM, or like a recurrent neural network structure, that gives you proposals for each of the latents in your simulator, taking the observed data as the input. So this thing is the forward simulator. You invert it by taking the output and making it an input to the proposal. So the proposal, like at inference time, when somebody gives you an observable y, you give this to the neural network, and the neural network knows what to propose to each of the random numbered throws that can happen in the simulator. Yeah, it's a bit more involved than that, but I think this is enough detail. Yeah, and you train this thing by this KL divergence-based loss there. Yeah, so yeah, this is about the protocol part. So this thing is based on flat buffers. It's something like protobuf. If you are familiar with that, you would know what I'm talking about. It's like a language-agnostic protocol where you can connect to from any of the supported programming languages, these ones you see here. And this is somewhat similar to the ONNX thing in deep learning, people have this protocol for exchanging trained neural network models between different libraries. This is serving a similar purpose for the pro community. If you can connect your probabilistic programming system to this protocol, through this protocol you can connect it to any of the simulators that are connected to this protocol. It's like a middleman, where like probabilistic programming systems connect from one end and the simulators connect from the other end. Basically, this allows you to execute different models with different probabilistic programming systems without the requirement that you stay in one system. And in practice, this works by, again, like this sort of thing where in the bottom, so this is a simulator. Every time you have some stochastic activity, you need a random number draw. You go through the protocol, you ask for a random number. The probabilistic programming system gives you the random number, and it also does the bookkeeping that I was talking about. So from the simulator's perspective, everything stays the same. You just make a call to a random number generator. You make a random number draw. You get your random number. You are happy. You keep going. But behind the scenes, you have some other things happening in the proc system that does trace recordings and does like runs MCMC inference and other things. That's basically the software engineering part of this. And this is another way of looking at what is happening, where on the top you have the yeah, Kyle likes this. It was his idea to have this puppeteer, or yeah. So the idea is that the machine learning or probabilistic programming system is controlling the simulator at the points of random number draws, basically by having a control of what is returned here as the random number sampled from the distribution. You can direct the simulator in ways that make it likely to produce observations, like simulated observations that are similar to real observations. This is what's going on in posterior inference. So the simulator is controlled by the machine learning system through the stochastic sampling interface. Yeah, this is just showing you a bit of C++ to show that like this is how it looks like in C++. So you basically have this very lightweight thing where you include that file and you get these like distributions, sample statements, and conditioning things. So for example, this is a conditioning here. Okay, so the reason we did this C++ thing was we work in the high energy physics setting with very large scale simulators of particle physics, and they were in C++. So we have all the system available in C++. And the project is called Atılım, as I told you. This is very like it's a very difficult to see thing, but it's simulated spelled backwards. That's like a code name for the whole effort. Yeah, this has been a very large distribution by, collaboration by machine learning standards. We have all these people involved, and at some points we had to run code on a supercomputer to get these like millions of execution traces I referred to previously. So this is about that. Yeah, so if you are interested in this, there are basically two papers that you can have a quick look at. So the one on the top is the machine learning aspects of this, and it's at NeurIPS this year. And the one in the bottom is a supercomputing conference. This SC19 thing is like the main place for supercomputing work. And we got nominated as the best paper finalist this year. I don't know what's going to happen. It's next month. They are going to decide. The reason for that is like the simulators are very costly, and you are supposed to run things very large scale. For example, at some point we had to run like 30,000 CPU sampling from this simulator and training the neural network. Yeah, and for people interested in this or like using these simulators, so we worked with the simulator called Sherpa, and this is the actual like entrance. How can I say, the main method of our C++ side. You can see things like where you do the likelihood. For example, this is the likelihood piece here. That depends on, like you run the simulator, you extract some interesting physical things like the moment of particle and like particle decay types and things like that. So these are your interesting Laytons. And at some point you have a simulated calorimeter, and you construct the likelihood from the simulated calorimeter, and you get the real, like the observable calorimeter value that you condition on. You evaluate it under this likelihood. So this is the whole entry of the simulator. So some interesting things that I can mention here is like when you work with the large-scale stochastic simulator, this is very different from the usual probabilistic programming setting, where people have been working with toy problems mostly. So because in this type of simulators you can have tens of thousands of Laytons, and there are cases where you have very unlikely cases in the prior, like the question before. For handling this, we are coming up with different tricks. One of them is this thing called prior inflation. Basically, if you have a prior that looks like this, and some of the things are very unlikely, in the learned proposal setting, we don't use this prior. We make it an uninformative prior, like we basically even out all the probabilities in such a thing. We generate things from this distribution, from the overall the simulator. We train the neural net with this type of data, so that the neural network gets to see like unlikely cases as much as it sees likely cases. So that's not the real model, but we can use the neural network trained this way as the proposal at inference time using the correct prior probabilities. And if we account for all the factors, basically you do inference in the correct model using a neural network trained in the prior inflated model. So it's like to give you an idea of what type of tricks we are supposed to come up with, like working with real simulators. So this is one thing. The other thing is, actually this is like the biggest difficulty we are currently working on, is the rejection sampling code in simulators. It's very common to have loops of sampling and some condition, like you keep sampling stuff in the simulator in a loop until some condition is satisfied. Most of the time these are rejection sampling loops. Other times it can be population-based simulators where you like loop over some like very large number of samples. These things make it for people who know about probabilistic programming, these things make your execution trace extremely long, and this is very difficult to handle in existing probabilistic programming systems. And we had to come up with some extra things to handle this. So I will show you some experiments in the particle physics case I was talking about. So we've been working on this problem where you have a tau lepton decay. So one of the Laytons is this decay channel. It's difficult to read here, but like tau lepton can decay into different things, and I think there are 38 cases. And these are prior probabilities over these decay events. And like this is a logarithmic scale, so some of these things are extremely unlikely, so as we talked about before. One thing I didn't really talk about is the notion of addresses. So in the simulator, you are supposed to distinguish between different random numbered rows. So you are supposed to, for each of your latent variables, you are supposed to be able to uniquely label each random numbered row in the simulator. And this is based on stack traces. So you see two instances of this. So you can read this as A1 is the address of the first latent in the simulator. And you identify it by this label, which is a concatenation of the stack, meaning, so this thing starts in the beginning by the function that starts all the execution, that forward function. You keep following this. If you know the simulator, you can also separate this into different like interpretable like call graphs. Basically, you start from one function, that function calls the other function, you go to some part of your simulator, that part calls another part. You can really follow these things because you have the whole simulator available to you. So people who know Sharp, for example, in our collaboration can see that, okay, this is doing this type of particle event. At the end of all this like calls, at some point, somebody asks for a random number. So, for example, this one is asking for a uniform random number at the end of all that series of calls. So this is one uniform random, continuous uniform latent variable. This is an example where you end up requesting this decay event, like the decay channel Laytons, this A6 here, over 38 different ways of decaying, so that I talked about. So again, by looking at this thing, or like this is a concatenated list of function calls, but you can separate these and you can see where you are in the simulator and like why you ended up making that random number throw. Basically, this is your way of connecting the simulator code space to your probability model space. These things are the bridge between these two worlds. And the traces in practice look like that. The traces are like sequences of such random number draws for your Laytons. So I'm showing you here some Laytons that are interesting from a particle physics point of view. So basically these three momenta and the decay channel are interesting. So we are, so this is the prior plot, and you see the prior decay probabilities. And the thing we condition on is we have the real Sharpa simulator coupled with the little particle detector simulator, custom written. And this particle detector gives us a three-dimensional, like the volumetric thing, 3D observable. This is how it looks like. I mean, it's not the greatest graph, but like you have some voxels in this space. You condition on these voxels, and you are trying to infer like the posterior conditioned on that simulator data. You get the posteriors over all your Laytons. And this is a prior, this is a posterior, and the vertical dashed lines here are basically we test this with simulated data. So this observable particle detector output comes from the actual model. We sample one trace from the prior. This we plot them here, like the dashed lines. So these are the values that gave us that observable. But from that test case, we only keep the observable. We pass that through our inference system, and we get the posterior distributions. And we see that like the posterior recovers the correct values. This is how we evaluate the system initially. So this is an MCMC posterior. I forgot to make that point. And this is very costly. And for example, this one, even though it looks simple, it requires like days of running inference with the MCMC engine. And this one is based on about 7 million simulator runs during the posterior inference phase. And the way we know that this thing is the correct posterior is we run several, or at least 2 posterior inference sessions. One starting from starting from different places, and when you run them long enough, your histograms, like there are two histograms here for each latent, they converge to the same thing. And you can also do things like looking at convergence diagnostics, like the Gell-Rubin diagnostic or autocorrelation and other things, to like run many MCMC inference sessions and convince yourself that you converge on the real posterior and you are sampling from the real posterior. So, and this is showing you the autocorrelation time for the simulator. It is about like to get uncorrelated samples in the MCMC inference case, you need 10,000. Around 100,000 runs between your executions. So this thing is to make the point that you sample in the execution spaces, execution traces, sorry. So this thing is just like a subset of the whole latent space. The whole latent space looks something like this for most of the observables. Like you get posteriors over all the stuff in the simulator, thousands of addresses. So I couldn't resist putting this here. So at some point I was presenting this, I think earlier this year in the dark matter event. So one of the organizers tweeted me with this slide and made like a little joke that this was the largest number of histograms ever put in a slide or something like that. Then this is Lucas Heinrich, one of our collaborators, and Carl's PhD student, no longer PhD student. He was like he did this little joke by like putting a bigger one and putting that tweet here. So I couldn't resist like doing this and adding one more level to this recursion running joke. But maybe I think we should just end this here. Yeah. Yeah, so I'm there, so somewhere there in this inception-like thing. Yeah. Okay, yeah, so this is the part where I come, like, I mean, like I'm coming to the conclusion. So the idea with this like neural network-based inference is that your sample efficiency is very high. And this thing, one point actually I forgot to make is in the importance sampling family, you don't have the autocorrelation, you don't have the burn-in problem. Basically, it's embarrassingly parallelizable. So it means you can run many instances of such trained neural networks, and every sample you get is an uncorrelated sample from the posterior with the correct weighting. So this is for making that point. Again, about like the main theme of this workshop, the interpretability thing. I mean, one of the main themes. Because you work with the model and you have these like deep connection to the internals of the model, you can do interesting things like this. So this is these are the random number, like the latent variables. For example, you see the A1 and A6 I referred to before. So this is the beginning of all the traces and the end of all the traces. So I construct this type of graph by running the simulator many times and collecting the statistics of what sample is following what other sample. So you can do this type of things, and you see like these things are always following them in the same sequence. But here you can have from this you can go to that or do other things. So this thing looks like a state machine, but it's not a state machine. It also looks like a bit like a graphical model, but it's not a graphical model. It's a address sequence graph where you see the overall behavior that you can have in your simulator. And like you can identify different parts of your simulator in this type of graphs, and you can see like what corresponds to what and what part of the simulator is responsible for what type of your posterior result. Another interesting thing is like this one is made by looking at the 10 most common trace types. So this is the picture that you get from that. It's not very, I mean, it's not crazily structured. But if you take more trace types into account, you get more and more detail show up in this type of graphs that shows you the latent structure implemented in the simulator. Basically, by doing this, like with more traces, you slowly discover the latent structure of the simulator that is already there in the code base, but in a way that even the people who implemented this simulator were aware of. For example, we were talking with the Sherpa developers. They were very excited to like be able to do these things and condition on some parts of the simulator being executed, because this gives them like a way of finding cases that end up coming to that part of the large code base. Yeah, so this is an interpretability related thing. Another thing is like, so you can make these things for different distributions. What I'm trying to say is like, so the one on the top is the prior one. It's difficult to see here, but there are like numbers here that represent the frequency of these jumps between latent samples. And these are different in different distributions. For example, this is the one in the posterior where you see some parts are different from the prior. And you can interpret that for this type of event, you are more likely to have this type of explanation in your simulator. I have to give more details about that later at another talk. So what we are currently working on is like, most importantly, we are working on this like using this API or like the interface for learning simulator surrogates. Some people are working on this. And the other big thing is the rejection sampling stuff that I talked to you about, like that is responsible for making very long execution traces. And another thing is that I also end up putting this here. So this is like one of these graphs. This is how things look like when you have a bad case of rejection sampling. Basically, this part is the center part here. Basically, all these loops here, they represent rejection sampling instances. For example, I know this one. This is the part where you, it's difficult to see here, but there's like a color change here. You get like a number of samples and another color, number of samples and another color. So these yellow colors are responsible for Metropolis Hastings acceptance criterion. I know that in the code. So this whole loop is basically a loop running to satisfy some condition. So you can look at these type of soft structures and understand like the structure of your model. Yeah, and these are other loops. Yeah. That's where I want to finish, and I wanted to tell you briefly about this. So we have this workshop at NERPS, Machine Learning and the Physical Sciences. We have a group of interesting talks. So if you are around, it will be good if you could attend this. That's basically it, right? So yeah.